takes energy from itself. That means its temperature and pressure drop. So what you have here is a atmospheric pressure and low temperature air. So this low temperature air is sent to the cold room where it can provide refrigeration, cool the products and all, and in that process it picks up some heat and its temperature increases, and from here again it goes back to the compressor and this cycle is repeated. This is what is known as the open type air cycle refrigerant system, and as I mentioned, this is mainly used for providing air conditioning in aircrafts. This system is not very efficient and it's also bulky, but why we use this in aircraft is that the components required for this system, typically the compressor and turbine, which are the main bulky components, are already there on the aircraft. So an aircraft engine requires a compressor and a turbine. So instead of adding a fresh compressor and turbine for the air conditioning system, you can use the existing compressor and turbine. So this is the reason why this system is mainly used in aircraft air conditioning systems. And you can also have a closed cycle refrigerant system using gases, in principle anything other than air. You can also use other gases. For example, you can use helium, okay, or any other gas. Now let me discuss another important and commonly used refrigerant system, what is known as vapor jet refrigerant system. This here also it's also a vapor cycle. That means here also you produce refrigeration by evaporation. But again, the major difference between this and compression system lies in the way in which you maintain the pressure in the evaporator and the way in which you compress the evaporated vapor. So that's where the major difference lies. The basic principle I'll explain here. Whenever you have okay, I will show the schematic a little later, but let me just explain the history here. The first vapor jet refrigerant system was designed and developed by French engineer Maurice Leblanc in 1907. So he has used steam. Then in Westinghouse has commercialized these systems in 1909 in Paris. And from 1910 onwards, these systems have been used very widely in warships, breweries, etc. And the Russian engineer Badel has developed closed cycle vapor jet systems in 1955. So he did not use steam, but he used other refrigerants for providing the refrigeration. Let me explain the working principle of this. This is a typical steam jet refrigeration system. What we have here is an evaporator drum and a condenser drum. So this is a condenser drum and this is an evaporator drum. This evaporator drum consists of water, and this condenser drum also consists of water, and the motive force or the prime energy input to this system is in the form of motive steam. Motive steam means high pressure steam. So when this high pressure steam flows through this nozzle, its pressure reduces and it gains kinetic energy. That means at the exit of the nozzle you have a fast moving motive steam. So because of its high velocity, it can entrain the vapor from this drum. That means whatever vapor is there in this drum gets entrained by this fast moving motive steam, right. So vapor is removed from this drum. So once the vapor is removed, more vapor is formed by evaporation of the remaining water. That means the water evaporates to provide the continuous vapor. So as a result, rest of the water gets cooled because evaporation is endothermic. So you have production of cold water here. Okay. Now what happens to this vapor? This motive steam plus the vapor that is evaporating in the evaporator both get mixed and then they flow through a diffuser. In the diffuser, what happens is you convert the kinetic energy back to pressure. That means at the end of the diffuser you again have a high pressure steam. Okay. This high pressure steam now comes in contact with the cooling water that is flowing through this heat exchanger. When it comes in contact with the cooling water flowing through the steam, it rejects the latent heat of condensation and it condenses. So ultimately you have condensed water here. That means you evaporate the liquid water in this evaporated drum using the motive steam and then condense the motive steam and the evaporated vapor using a diffuser, increase its pressure in the diffuser, then using cooling water you take the heat out of the vapor and condense it. Then to complete the cycle, what we have to do is we have to again split this liquid into two parts, and you have to send the makeup water back to the evaporator drum, and the rest of the water again has to go back to the boiler feed pump to complete the circuit. This is the principle of a steam jet refrigeration system. And we use here, as you can see, we don't use any mechanical compressor here. The mechanical compressor is replaced by a combination of a nozzle, ejector, diffuser and all. So this is sometimes known as an ejector refrigeration system. And the principle of ejector was actually used in the beginning to pump out air leaked into the condensers of power plants. So this is the first application of ejectors. Later the same principle was extended to the refrigeration systems. In principle, you can use any other working fluid other than steam. You can also have closed cycle systems using refrigerants. Okay, you need not use. If you use refrigerants, you can produce lower temperatures. When you are using water, you can't get temperatures lower than 0 degrees centigrade. That is one limitation of water. Okay, these systems were used in the beginning in several, as I said, in warships and breweries and all. And this is also used for providing what is known as vacuum cooling in food products. That means in the evaporator drum, what you have seen earlier, you can put the food products itself and take out the moisture from the food products using an ejector. So when you are taking out moisture from the food products using an ejector, the food products get cooled. Okay, so this is the principle behind vacuum cooling, right? So this is the steam jet refrigerant system. Now let us look at thermoelectric refrigerant system. So Seebeck effect. Seebeck effect is reported in Germany, and I am sure most of you are familiar with Seebeck effect. Anyway, let me just recapitulate this. What we have here is in a Seebeck effect, you have two dissimilar metals, and when you maintain these two junctions, you have let us say that a metal A and a metal B, and these are the two junctions. And let us say that you are maintaining these two junctions at two different temperatures. Let me say that you have this junction is a hot junction and this junction is a cold junction. So once you have two dissimilar metals joined together, and when you are maintaining the junctions at two different temperatures, an EMF will be developed in the circuit. That means you will see that a current is flowing through the circuit. This is what is known as Seebeck effect, and this is reported in Germany in 1821. Next, Peltier has found an effect which is the reverse of Seebeck effect. Okay, this happened in 1834. So let me explain what is the Peltier's effect. You have seen the Seebeck effect, and let us look at the reverse Peltier effect. That means you have, let us say that again two different materials A and B. Okay, and now let us say that you are passing electrical current through this. Okay, you connect it to a battery and allow current to flow through this. When current flows through this, that means when electrons flow through this, you find that one junction becomes cold and the other junction becomes hot. That means by joining two dissimilar metals and by allowing current to flow through this, you can produce refrigeration at one end and you can reject heat at the other end. So this becomes, let us say, hot end, and this becomes your cold end. So you get refrigeration effect at this point. So this is the principle behind Peltier effect. So using the Peltier effect, Lenz has actually demonstrated the Peltier effect by freezing a drop of water in 1838, and he has used bismuth and antimony as the materials. But later it was found that metals are not really the ideal materials for use in thermoelectric refrigerant systems, because of as you know very well, metals have very high electrical conductivity which is required in a thermoelectric system, but they also have high thermal conductivity. Because of the high thermal conductivity, it is difficult to maintain the cold and hot junctions at the particular temperatures, because heat will always flow from hot junction to cold junction, and since the thermal conductivity is high, the temperature gradient tends to reduce. So this is the problem with metals. That means metals typically have low, what is known as a low thermoelectric powers. So if you want to develop a good thermoelectric system, you have to have a material having high electrical conductivity but low thermal conductivity. For almost 100 years, people could not find any suitable materials However, in 1940s, people have invented semiconductor materials, and semiconductor materials have reasonably high electrical conductivity and low thermal conductivity. That means they have high thermoelectric power. So now you can, the systems are ready, you can make thermoelectric systems using semiconductor materials. Semiconductor materials typically, you know, that have P type and N type. You can have two types of semiconductor materials, P and N type. So a typical semiconductor thermoelectric element consists of a P type element and an N type element joined together. So you have two junctions joining the P and N type elements, and when you give a power supply, a DC power supply at low voltage, electrons will flow, and when the electrons jump from P to N, they absorb energy, and when they jump from N to P, they reject energy. That means you get a cold junction on one side and a hot junction on the other side. Okay, this is the principle of semiconductor based thermoelectric reference system. However, you cannot use just one P element and one element, because the cooling that you get with just one element is too low of any to be of any practical use. So in practice, what is done is you stack a large number of thermoelectric elements in series, and you make a thermoelectric module so that you can produce a sizable amount of refrigeration. Okay, so this is the principle of modern day semiconductor based thermoelectric devices. And later, actually, the Russian scientist Iov is one of the major pioneers in the area of semiconductor based thermoelectric systems, and Russia has developed several domestic refrigerators using this principle. And in USA in 1960s, they have developed large air conditioning systems using the thermoelectric principle. One major problem with thermoelectric principle is that the efficiencies are typically low compared to vapor compression systems. However, they have the advantage that they are silent in operation, and they are very reliable because you are not really using any mechanical component there, and you can use the same thermoelectric module by changing the direction of current electron flow either for heating application or for cooling application. This is one of the advantages of thermoelectric systems. Now let me show the working principle of a thermoelectric module. As I was mentioning, it consists of a P element and a N element. So this makes one thermoelectric element. So several such elements are stacked in series, and this forms a thermoelectric module. And all the cold junction are collected on one side. So this is the cold junction, and all the hot junctions are connected on the other side. Now when you connect this thermoelectric module to a DC source, let us say at 12 volts, and when you start giving the power supply, electron will flow through the P and N elements and through the thermoelectric module. And as I mentioned, as electrons flow from P to N, they produce a cooling effect. So you have cooling on this side. Okay, and when it flows from N to P, you get a heating effect. So you can see that this junction is hot. So by designing them in this manner and by stacking them together, you get cooling on one side and heating on the other side. Okay. And of course we have to have some electrical insulators to avoid shorting and all that. And as I was telling, depending upon your requirement, if you reverse the current flow, you can use the same side for you can have either cooling on this side or heating on this side just by reversing the direction of the flow. So this is the principle of your thermoelectric reference system based on semiconductors. Right now these systems are used in small portable as small portable refrigerators. For example, you can carry it along with you, okay, and this is also used for carrying vaccines and all to remote areas. These are the main applications of thermoelectric systems at the present moment, and they are also used in certain high efficiency computers for cooling the computer chips. Now let us look at another interesting system called vortex tube system. Let me again explain the working principle of this. This is a very simple system. What you have is a tube, a long tube with a valve on one side and a central hole on the other side. And let us say that using a nozzle, this is a nozzle, and through this nozzle you allow high pressure air, high pressure. So when you allow high pressure air through to enter into this tube through this nozzle, at the end of the nozzle, at this point the pressure is converted into kinetic energy. That means its velocity increases tremendously, and when this high velocity air enters into this tube, it undergoes a swirling motion. So you get a swirling motion. So air undergoes a swirling motion, and during this motion and during its passage from one end to other, a cold core is developed near the axis. That means you have a cold air stream at the axis and hot air stream around the cold air stream. So you have near the periphery you have hot air, and in the central portion you have cold air. So the hot air escapes in this through this, and the cold air comes out through the opening on the other side. So this is known as a counterflow type of vortex tube. So you can see that what you need here is a simple tube and a supply of high pressure air. All that is required is that, okay. And depending upon the valve position, you can get different temperatures of cold air and different amounts of cold air. So this is the principle of vortex tube refrigeration systems. Vortex tube refrigeration systems are not very efficient, but they have certain advantages. For example, it's very simple, and all that you need is a compressed air supply. Okay, so that's why these systems are mainly used for cooling machine elements and all. For example, in machine tools, you want some localized cooling, you can use a vortex tube, and you supply compressed air to the vortex tube and get the refrigeration effect. And this is also used in jackets worn by the miners. When the miners go into deep mines, they require cooling because it's very hot in the mines. So they can carry the vortex tube in their jackets, and the vortex tube is typically connected to high pressure air supply, and they get cooling because the jacket supplies cold air to different parts of the body, and the different parts of the body get cooled. In addition to this, you can also supply the fresh air continuously to the miners. So this is the advantage, and this is the reason why vortex tube systems are used in mines. And as I was mentioning, in 1931, George Rank has discovered the vortex tube effect. And in 1945, actual principle behind vortex tube is very complicated. I mean, the analysis is also very complicated, and for many years, even the people have demonstrated the effect, they could not really explain the physics behind the vortex tube operation. And in 1945, German physicist Rudolf Hilsch has given a scientific explanation for vortex tube effect. That's why the vortex tube is sometimes known as Rank and Hilsch tube. And since then, as I was mentioning, this is mainly used for spot cooling in machine elements, in electrical components, and also in mines for cooling the miners. Now let me conclude this lesson. We have in this lesson we have defined refrigeration and air conditioning, and we have outlined the historical aspects of various natural and artificial refrigeration methods. And while doing so, we have also explained the working principle of these systems in brief. And when we discuss these systems, we will explain the working principle once again in detail. Okay, and right now the main focus is to develop refrigeration systems. The modern life, you cannot imagine modern life without refrigeration and air conditioning. It has become an essential part of our life. So almost all the industries require refrigeration or air conditioning, and we need air conditioning for thermal comfort. So air conditioning systems are very widespread, and it is almost a common item in all households in the form of a domestic refrigerator. So what are the issues right now with refrigeration and air conditioning? The main issues are developing systems that are energy efficient, because typically in a refrigeration system or air conditioning system requires energy input. So you have to make systems which are efficient, energy efficient, and there are also certain environmental issues related to refrigerant systems. So whatever systems you develop should be environment friendly, and they should be affordable. If you want to make it available to everybody, you have to make them affordable. So these are the main issues, current issues in refrigeration development, and the studies are going on these aspects, and we will discuss these aspects in detail in subsequent lessons. Thank you.